Welcome, everyone. My name is Ishan, and we're here today to present some learnings about how to compile Kotlin really, really fast on a super large project. Next. And then for the agenda, really quickly, we'll do a little bit of introductions, and then we'll kind of tell you why is it actually important to even think about build speed, what challenges we've faced, and how we've tried to solve them. And then by the end of it, you'll probably learn how to compile it at least 1.5 times faster, if not 2 times faster. But I'll give it to Pengwen to take it from there.
Okay. So I am Pengwen. I'm a tech lead of TikTok Azure engineering infra team in the US. I'll be working on the Azure compilation, toolchain development, and maintenance for about 5 years, which include TikTok forked Gradle, Kotlin, and HP version, which contains the dozens of optimizations we built for efficiency and quality enhancement. Also, I've been in charge of TikTok's whole DevOps lifecycle efficiency improvement for about 3 years and I pushed TikTok move from multi-repo to mono-repo and make the full source code compilation mode with a powerful support of compilers. And then, Ishan?
Oh, I'm the tech lead on the mobile architecture and infrastructure team here in the US. But as for my introduction, I'm just somebody who constantly bugs Pengwen with a lot of build issues. And that's what led to the idea of actually coming out on the stage. Back in droidcon San Francisco and now at droidcon New York, I was like, if you're answering these questions to me all the time, why don't we share these learnings with other people so maybe they can take something away? So how about first, Pengwen, you introduce what's the scale of our project like?
Sure. Yeah, first, TikTok project is a very big monorepo, which share the modules between different products. We have several metrics products inside of TikTok company. And we already modularized the whole app, and all of the 5 million of code split into about 1,000 modules. And then, as I mentioned just now, we are now use a full source code compilation. To be honest, it's not an easy job to make such a big amount of code compiled runs rapidly every day. What's more, to maintain such a huge project, we now have about 600 of Android developers who triggered about 6,000 of build every day.
Well, those are some big numbers, and we kind of understand that with a lot of engineers in a large project, this is a hard job to consistently deliver on like infrastructure and developer experience. But nowadays we've got like powerful machines and a lot of infrastructure that we can actually spend money on. Why is it even relevant to talk about build speed?
Okay, according to our monitor metrics, every 1% of build speed increasing could bring 1 million human power and build machine cost saving every year. Yeah, it's not actually seems like a big number, but it's not because we have 6,000 of build per every day, and it's clear that so that's clear why build speed is so important to us. And besides of the direct money saving, build faster could also make significantly let developers do features they test more often. Of course, you can test it in minutes, and it will be different if you test it in minutes and hours. So which will also let we deliver our features better and faster. And also, the build speed can highly related to the developer's experience. Imagine that if you spend 2 hours every day to wait for the code building, it's definitely not a good experience, right?
It is not, and it's also not good for your health. I find myself drinking a lot more coffee while Gradle's either indexing or building stuff. Okay, we've established that having an improvement in the build speeds, you could have measurable cost savings for engineering teams in terms of both time, productivity, experience, satisfaction. And so it makes sense to invest in the optimization of this kind of aspect of your build tooling. But how do you actually optimize the builds?
Oh, that's a good question. Yeah, my team puts a lot of efforts on this part, and we have lots of successfully wins. So let's share some of things. To optimize the build speed, our first answer is always make single file build faster. Guess how we do that?
Well, you basically have a bigger machine, like a much powerful machine, maybe, I don't know, M27 something like that?
Yeah, sure. Yeah, the easiest way to do that is pay to win. Yeah, to upgrade our machines to make the build faster. Yeah, just a joke. In fact, when we first plan to optimize the build speed, all developers come with this idea that say, oh, why we don't provide us a better machine, and it can significantly improve the build speed. Yeah. But why we didn't try this? Actually, we really do this. Yeah, but the problem is, for such a big project, the scale increasing rates of the project is always much faster than the machine hardware upgrade. Imagine that you upgrade the machines every year, and it's 20% build speed increasing, but the code scale is always almost more than 20%, right? So the increasing rate of the project is always bigger. And so it's an easy way to do, but it's not a continuous way to improve the build speed. We need to find another way.
I understand. So then what else do you think we should do? I see we should reduce the amount of compiled code somehow?
Yes. Actually, in the past few years, there's a traditional method to achieve it for Android. Some of us might know we use binary mode to optimize the speed, that we're trying to publish part of the project code into binary ARs so that the others can just build without this part of source code. They use AR directly. Yeah, we also tried this, and it did work to improve our build speed. But it's also brought tons of side effects for us. For example, it didn't work well with the Gradle cache system. Yeah, you can imagine that if you switch from binary to source code every day, how the Gradle cache system work. And it's also not good for the ID symbol and analyze system. It will make just so many errors in your editing page. Also, it's not compatible with some new completion features like the sugar and the Kotlin method inline. So finally, because of there's so many side effects, so we finally give up this solution.
Oh, but then I've heard a lot about Gradle cache, and like you can also talk to a bunch of Gradle engineers out here who always tell you to use the Gradle cache, the incremental compilation, and all those things. We can just leverage and improve the builds. Why do we need to spend 30 minutes here listening to your talk?
Yeah, it's clear that cache and incremental is not a fresh topic. Everyone knows that. But how to maximize the cache hit rate and reduce the more build task from the regular compilation is still an ongoing problem we need to face every day. So I'd like to share 4 practices we made which helps the project make a better usage of build cache and incremental build.
Well, before we actually dive into that, do you remember our first conversation when we were down like 4 cups of coffee and you were trying to tell me why the build is working the way it is and like what all those crazy statuses from the Gradle builds were, so that when we talk about the improvements, people can actually understand what those Gradle statuses mean? Okay,
cool. So let us better understanding of the next content, I will share briefly talk about the Gradle task system. Gradle split task into several status that's executed, up to date, from cache, skip, and no source. Yeah, and these 3 are the most important ones that's executed. Executed just means the task runs as usual, and the up-to-date means it's a full incremental build. Nothing changes, and it's used to output directly. And from cache just means Gradle try to calculate the input and get the output pack from remote service or local storage, and directly then skip the task execution.
I see. So what you're trying to say is if I hit something over and over and over and over, I'll get the result faster. And in this case, the up-to-date is the status I'm looking for, and then also the from cache status?
Sure. If we have more up-to-date and from cache, of course, our build will be faster. So let's begin our first optimization to let the build from cache and up-to-date more. Actually, it's the simplest one, but it's also the one we always ignore. So it's the unusual dependency removal. Start from one simple case. For a Gradle project, Gradle normally compile the array modules, build a Gradle file, and build the task graph in the configuration stage. We know that we have such a stage in the picture here. After that, Gradle will execute all the tasks one by one according to the task graph and takes Kotlin compiler task as an example. The upstream node Here we means the A, module A, requires the downstream task output artifacts like the ABI info, classifiers, and as it input. So that's why we have to build it in order strictly, because we need the downstream modules output. Every upstream module doesn't use anything, even though the upstream module doesn't use anything in the downstream module, because Gradle doesn't know that. And because it's not predictable, so we always need to build a downstream module. So the structure could be just fine when it's first designed, because when we're trying to add a dependency, it's always used. But with our daily working and some code migration or mode, so as a part of the dependency stage might become unused. So for example, in this dependency tree, there's already no direct reference between module B and module C, and module C and module E. But if we still leave the dependency age there, declare in the build file, so the task graph will still have 4 layers, and of course it will compare them one by one. What if we remove the unused age? The new task graph will be like this. Well, it's just the 2 layers. So besides of this task, complex dependency tree can also affect the incremental build rate and the catch hit rate. So we recommend all project owner could just scan all unused dependencies regularly and make sure it's always healthy.
I see. So how can people find out about the unused dependencies in their project?
Yeah, here we propose some way to help you recognize dependencies in your project. First is the Gradle internally, we provide a Gradle dependency task, so it can help you generate the dependency tree and then analyze it manually. Also, you can use the official recommend tools. Here we call the dependency analysis, and it can help you get the unused dependency age, and you can move it, and you can scan it every day and move it regularly. And congratulations, we've already finished the first step of optimize our project.
Well, this is amazing. I mean, if flattening the build tree helps, what if we were to actually start breaking down the tree itself so that we can further reduce the amount of dependencies or modules that we have to work with?
Of course, yes. Yeah, we know that unreasonable project structure design can always bring terrible maintenance cost for us. It causes a similar harm to the build speed.
So if my project structure, and it's an example, if my project structure looks like this, it's horrible, I know. Can you show us what impact this might have on our build speed, and if we can actually make any improvements to this?
Sure. First, let's see the base module. It's a common layer that in product that we put some shared code inside, and there's maybe some data models and some common UI and some interface here. And it's convenient. It's very convenient to solve dependency problems. Like if you put in different modules, you may face a circle dependency, and it will take some time to solve it. So you may put them in the shared module directly. But when there's some code needed to be shared between modules, you can put it here. But it could be also risky. Like when the time goes by, when we maintain the repository, the base module could become bigger and bigger, and the class inside is not common anymore. Like it can be shared just in 2 modules, but not all projects. At that time, modification to this module could easily make the unreasonable upstream module cache missing and recompile. In such a real project, it's not easy for us to declare whether a module is such a base module, but we can declare a standard to measure how big possibility a standard can how big possibility one module can make other modules unexpected recompile. So that's a metrics we figure out. We name it a single responsibility score. Yeah, the score contains several parts. Yeah, take the biggest base as an example. Yeah, module business image and the business network contains 2 direct dependency age to the big base. For each of the dependency age, we calculate its use reference count and the export reference count. The use reference count here means the classes we rarely join the upstream module compilation, which is class A and class C. And export reference means all classes symbol in this module provide. Here we means A, B, C, and D. And then we can summarize the average score of the big base, which tell how many percentages of the classes in the module has been really used by the upstream. Yeah, so once we get the score, we can try to decouple the modules from the highly score to the low score. After decouple, every module of modification will only affect the limited upstream modules. Meanwhile, it can also help us to crack code from the same usage together. Like if we have all the code together, of course the score will be higher because it exposes the same usage to other modules. Here's the tips: don't be afraid to have too much modules. Yeah, that's a very common afraid of new engineers. That if we have too many modules, it will be hard for us to maintain this. But it's not. With the support of our modern build toolchains like Gradle and the new Kotlin K2, it's an easy way to optimize and easy way to maintain such a big product, and will also make your modification inside of your module can be predictable. So it's definitely a good choice to make modules smaller and as single responsibility as we can. Another problem is here is a business image module. As a deep dependency, every time it gets the modification, will make all upstream module recompile. Yeah, to avoid this happens, we put another score here to measure the effects of one single module modification bring to other modules. We name it as hotspot score. To find the hotspot module from our project, we can calculate each module's deepest dependency level and multiple its modification frequency. Like for this module, it's the longest dependency depth is 4, and we found that it's modified 20 times per month, so the score will be 80. And we also get the modules from the highest negative effects to the lowest negative effects. So we will get such a list to maintenance. But when we get the score, how to fix it? Yeah. So here we recommend to use something like SPI and DI. SPI just here means the service provide interface in Java. It's a.
I see. So this is dead, but I can just speak. So service provider and dependency injection forces developers to use like abstract interfaces or like decouple direct access between the modules. Mm-hmm. And you're saying that this decreases the modification effect that it has on the build graph itself. Mm-hmm. But does it also decrease the average module layers that we have and the modification effects overall?
Right.
Okay, so we covered a lot in this section, and tell me if my understanding is correct. So in terms of single responsibility, when we're thinking about our project, we want to make sure that modules are as isolated as possible and as thin as possible. And the more frequently a module changes, we want it to live at the top of the tree rather than at the bottom of the tree, because it's going to cause like a compilation of the whole tree that gets invalidated because of a change. And then, turn this on for you. Sure. Thank you. Still not on.
You can use this.
Yeah, I guess. Hello. It's dying. And then it can bring a big big benefit to our build efficiency. I'm really excited, already excited about these, and then also keeping the least export by using like SPI or a dependency injection framework to abstract the modules if and when necessary, mostly between API and implementations of those things. Is there anything in store for us that you've got? I remember I saw 2 more optimizations that you were going to talk about.
Yes, actually, the first 2 optimizations is about how to optimize the project structure to make the build faster, and and we still have 2 optimizations where we focus on the toolchain itself, and it can make the build much more faster. Okay, first look at this picture. Yeah, here we declare all the plugins in the root build.gradle. it's a very common usage, right? Yeah, everyone declare all the plugin in the root build Gradle and include all the necessary Android build plugins, Kotlin Gradle plugins, and some custom plugins we write. But when it work with the cache system, it makes troubles, actually. Yeah, let's look at an example. Yeah, back to the build status category. Yeah, here we can see the from cache status means when the task cache fingerprint hits a cache store key, Gradle will skip the execution and reuse the output directly. But how to calculate the fingerprint? How to Gradle calculate the fingerprint?
Is it really even possible for us to know how Gradle actually computes this fingerprint?
Yes, of course.
Why don't you tell us?
Yeah, Gradle cache fingerprint contains this some parts like the input value properties and the input file properties and the task itself implementation, and also there will be a condition called cacheable to figure out whether this task can be cached.
And as a developer, how do I get access to all of this information, like in my terminal or in my IDE somewhere?
Sure, there's a way called org.gradle.cache.debug. This can print all the details about the fingerprint calculation, and you can figure out how well it break. So back to the problem. Yeah, we just figure out when you're trying to put all the things inside of the root build Gradle, it will break the cache system. But how? Let's see a real demo. Okay, here we can see we have a project and we already clear all the local caches, and we're trying to build the top level module. And we can see, oh, sorry. And we can see it's up to date, and we're trying to clean it. It's from cache, right? It's that's what we expected. But when we try to declare all the plugins in root build Gradle, and sometimes we have to upgrade the version. Like we have some custom plugins, and we modify some logic, and we have to update it. Like here, I just downgraded like from 19.0.0 to 0.1 to 0, and we run it again. Here we can see all cache misses. Yeah. So that's a problem. Okay, back to the, oh, sorry. Oh, I see. Here, yeah. So, yeah, we may need to know why it happens, right? So before we figure out how to solve the problem, we can take a glass of Gradle class load system first to prevent classing such a big, huge build system from affect each other. Gradle design a complex class load system for isolation. Then please pay attention to the root build Gradle class loader. It's a basic class loader which every module level class loader extend, and it's normally used for the project level extension for plugin declaration. Then why we usually put all the plugin class part here? It's really convenient because it can be used for all the project level. But it's actually not a good practice, as we just see in the demo project. Imagine that if we have any change to the plugin list and the version, and then makes the whole project cache fingerprint changes, which break the cache hit globally. Of course, it's not what we want to see, right? The solution is also simple. We just move the library level plugin to its minimal scope, especially for those scope like we have some transform, we have some plugin to reduce transform for the app module. normally we put in the root level, but actually the transform only in the app module. So we should move it to the app module. And we can try if we do this in the IDE. Here we have the plugin, and we comment it and compare it. Compare it again from cache, right? And if we put the declaration in the top level, like we have this declaration, and we try to upgrade it. And we can see this here from cache. So that's what we want to see.
Perfect. So again, what I took away from this is that in order to improve the build using the class path isolation method that you name it, we should never put all the plugins in the root build.gradle file.
Right.
And we should always try to declare the plugins in the relevant module where you actually need them, not across the whole project.
Exactly.
Well, but a daily development scenario where I'm not changing any plugins and things like that, I'm usually just coming into the office, pulling the branch, the developer branch, and which I think would have been updated, all the caches would have been warmed up overnight. I pull it, I build it, and then I make some change. And that happens in like 40 seconds, whatever, like the first one. But then at some point of time, I make another change to the project, and all the magic that you just sprinkled disappears. And it actually takes a lot longer for me to build the thing, and the time was like 5 times more. Why did that happen exactly?
Yeah, it's wild, right? That's because many up layers module catch missing after you change the low-level module. When you first pour the code, because it's all matched someone other's machine, so the cache has already uploaded and you reuse all, but you change something and up layer modules has disappear. In fact, it's almost reasonable according to the Gradle cache calculation algorithm, but it's still a significant design issue in Gradle, especially for such a high frequent change and complex task like Kotlin compiler task. Because the input changes a lot and it's easy change. You change just one line file and the input file just changes and the cache miss. So according to our metrics, the average Kotlin compiler cache hit rate is just about 30% level under this condition, which is not flawless at all. And this also brings us to our last optimization and the most important one. We name it cached incremental. Think about this problem. Why Gradle cache output cannot be used for incremental build? Or what the difference is between cache and incremental? Here's the execution model for a regular Gradle task. Gradle trying to run those steps one by one. Once one step was accepted, and Gradle will skip the next step and use the hit step result directly. And from caches here, when all fingerprints matches, Gradle will put will pull the cache back from local and all remote repository and move it to the output directory, then skip the next executions. And incremental logic is here. As we can see, it's totally a self-implemented logic. Actually, this just many tasks don't have incremental logic, so it makes our build slow. And but as a modern compiler, Kotlin writes its own logic to implement the increment build histories. So we are very close to the answer why the build cache is different from the incremental. When we try to dig into Kotlin compiler incremental logic, we will be able to find that Kotlin uses a set of intermediate file to record the build histories, and the compiler can resume the incremental environment when the next build. Normally, since there are the Kotlin custom implements and Gradle don't include this kind of intermediate file in the cache patch, so if we, even though we hit the cache, we put all the things in the output file, and but it didn't include the intermediate file, which contains enough information for the incremental build. So that's why when you're trying to change one line code, and the incremental and the cache or doesn't work. Then let's build a solution for that. This is a regular Gradle cache pack. which contains a compiled bytecode which automatically unzip to the module's output directory. Yeah, that's a Gradle internal logic. And we will also pack the required incremental intermediate file by ourselves and store it with the same cache key. That means when you're trying to pull the Gradle output files, and we will also pull the Kotlin intermediate incremental file, and it will make the Kotlin can get enough information for the next build, incremental build. And then repeat this process for all modules when trying to fetch the Gradle Kotlin cache, and the problem automatically solved. Although this upstream module still missing their cache after change, but Kotlin can automatically calculate the diff and just build the incremental part at this time, so it will be much faster, about just 10 seconds more. So that's a root cause of this problem and how we solve it.
Well, so custom cache pack, like our own cache implementation, it really sounds crazy, but does this mean that this is like a silver bullet and like we just use this and all the problems are solved, or like can we do something more?
Sure, we can. Yeah, it's not all the things. Based on this thinking, we build a solution that is totally a game changer on top of Gradle cache system. We all know that the problem of Gradle cache system is we need to keep hundreds of unstable parameters like the input file, like the properties, 100% same to find the right cache. Any changes to the parameters could make the cache pack outdated and discarded. But remember our slogan, we want to make the better usage of cache and incremental. So discard this cache is just a waste, right? And let's see our solution. We call it baseline cache. Yeah. To break the restriction of Gradle cache matching, we split the fingerprint calculate logic into two parts. One of them is a required part, which contains a compiler version, plugin list, and some other parameters which can make the cache cannot be reused at all. And another part is optional one. Like the file list, the dependency list, and those parameters can be submitted to the compiler as a diff and make it incremental. Then inside of the remove cache repository, we will incorporate this cache pack, which is strictly match the required parts and similar to the optional parts, and return the most closest one as its baseline cache. Next, we will compile the baseline cache pack, content, and the local source file one by one, because we get the list, and submit the different parts as a dirty file, which need to be recompiled. Then Kotlin compiler will receive all the property history, incremental record, and the dirty file list, and it just regards the diff as things you just changes and make the incremental build. Finally, this not completely matched cache pack can successfully apply to your build. And next, we just inject the logic into a regular Kotlin compiler task. If Gradle cache can just hit lucky, we won't do anything. But once Gradle cache missing, we will launch the Fusion cache matching and the incremental converter to speed up the build. There's one point here need to be attention. For capturing the build parameters from Kotlin compiler, we need to modify and recompile our own forks of Kotlin compiler. Yeah, it's a little black magic, right? But recently, we just trying to move this process from to an external Kotlin compiler plugin. Yeah, that's a KCP. We know that, and we can make the ability pluggable to any version of Kotlin, and it can be reused to any other project. So if you also wanted to build this optimization by yourself, you can try to use KCP. Okay, now let's just review the overall design of baseline cache. Yeah, besides of the regular Gradle cache, we will have a new system called baseline cache, which will first use the Kotlin compiler parameter to query the closest cache pack, and then put them into the right place, and then finally notify Kotlin compiler to handle the rest of dirty files. After applying this solution, our Kotlin compiler task cache hit rate increased from 30% level to 80% level. You can imagine how big improvement it brings to the build speed. What's more, baseline cache can also apply to almost all the tasks which support both incremental and cache, like ProGuard, like transform, and Dex builder, and so on, so many tasks. And it's improved up on the Gradle's strict cache hit limitation and takes the cache hit rate to the next level. So Ishan, finally, do you still remember all the 4 optimizations we make today?
I can try to remember. I think the first one is called remove unused dependencies. So we want to make sure like nothing that's actually being used in your compilation process should not be a part of that build graph as much as possible, and also try to flatten the structure whenever you can. The next one would be we want to declare the plugins in the modules that they're actually needed rather than the root project of the file, which is what you termed as class path isolation. And the third one was modularize as much as possible. Never leave the frequently changing modules at the bottom of your build graph so that you don't invalidate the caches up the tree. And then the last one is if you find yourself still being crazy about your build times, you can actually go ahead and try to modify the Kotlin compiler itself to get better cache hit rates. This may not be useful for like every company out there, but like when you have such a large team and you're actually doing a lot of builds, these micro optimizations might actually bring you some sort of a benefit. But yeah, overall, I think the first 3 is something that any project and every project should use. But what I wanted also to ask you, and so we can share that, is that once we did all of this, I'm pretty sure you benchmarked some of that. 2x is kind of an overall thing, but what were the real numbers that you can share, which we actually saw an improvement on?
Yeah, actually, this is not all the optimizations made, but the most important ones, especially the baseline cache. With the adjustment of the project structure, we increasing the incremental cache hit rate by about 40% after file modification. And with the classifier isolation and the baseline cache, our Kotlin cache hit rate finally increased from 30% level to 90% level. Yeah, with all the optimization we made. And the Kotlin average build time also decreased about 70% and made our build efficiency about 2 times faster than ever before. And previously, our build for a 4-time build can take about 20 minutes because some of the caches cannot made. But once we apply the baseline Kotlin cache, 140 completion could only take about 3 to 4 minutes. So this decreased by about 70%. So that's a very important improve for us.
Well, I guess that's what we had for you. If you have any more questions, let me know, and I'd love to come down and give you the mic because he'll be answering the questions.